All right. Now, if you're going to watch this video, you definitely want to have seen the previous video about radius of convergence. So if you haven't watched that already, check that out before you watch this one. But as I explained at the end of that video, after we find the radius of convergence, you'll then be asked to test the endpoints. So, for example, this series right here is just a really generic geometric series. So you can imagine if x was like 1/2, then our terms would be 1/2. We'd probably start at 0 actually. So we'd have 1/2 to the 0, plus 1/2 to the 1, plus 1/2 to the 2. So you can see that to get from one term to the next, we're just multiplying by 1/2. So that's what makes this a geometric series. And you want to be able to, you want to spot that quickly. X to the n is a geometric series. And this particular one is a Maclaurin series. It's centered around 0. If we had had x minus c to the n, then that would be a geometric series centered around c instead of around 0. But the point is, we already know from experience and previous rules we covered about convergence of series that as long as the ratio of a geometric series is less than 1, it converges. But what about the endpoints? So we know that between -1 and 1, this is probably going to converge. And in the previous video, we would have gotten r equals 1 for this puppy. But does that mean what about 1 and -1? So to show you what we're going to be testing, let's just take a look at the endpoints. So what we could do is plug in one, just pretend x was 1 for a second, and see if this thing converges for 1. Because so far we've gotten from -1 to 1. The question is, do I put a curved parenthesis or a square one? A square one would indicate that we're including 1, and then a round one, a regular parenthesis, would indicate we're not including that endpoint. So if we plug in 1, you can see the series we're going to get is 1 plus 1 plus 1 plus 1 plus 1, right, forever. So it's pretty obvious that this series does not converge. So we need a curved parenthesis on the 1. Then we plug in -1, we'll just get an alternating series, because -1 to the 0 power is 1, but then the first power is -1, but then to the second power is +1 again, third power is -1, plus 1, -1, so we just get an alternating series, plus 1 minus 1 forever. And even though that sum is not going to go to infinity, the running total will go from -1 to 1, from 0 to 1, 0, 1, 0, 1, 0, 1, so it has no limit. The series is not converging because it doesn't add up to a single number. It keeps switching between 0 and 1, 0 and 1 forever. So it turns out that for a geometric series, this is a very basic geometric series, our endpoints are pretty much always going to exclude, have curved parentheses, so we're not including the endpoints. But on more fancy series, we'll do the ratio test first, get the radius of convergence, and then we'll test the endpoints. But that's really just the only step we're adding to the end of these problems. So we've got find the integral of convergence. Now if you have a keen eye, you'll notice that this is actually just the same problem we just worked, but I'm just centering it around 1 instead of 0. So in this problem, c equals 1. But don't need to know that off the top of your head. You can just do the ratio test and see what happens. So for the ratio test, first thing is we just run the ratio test. So we need a sub n plus 1 over a sub n and take the limit as n approaches infinity. So that's going to be the limit as n approaches infinity of x minus 1 to the n plus 1 over x minus 1 to the n. So this happens a lot with the ratio test where the bottom power is 1 less than the top power. So we just end up with everything canceling except an x minus 1. So the limit as x minus 1 needs to be, the absolute value of that needs to be less than 1. When we get rid of the absolute value signs, now obviously this limit as n approaches infinity, by the way, but since there's no n's left, all the n's canceled out, then really it's just the absolute value of x minus 1 needs to be less than 1. And if to sort of extract this from the absolute value signs, we'll use the algebra 2 trick of just throwing an extra sign on there. So we have less than 1, but greater than -1 is the trick. So you just take whatever's in the absolute value signs. If it's supposed to be less than 1, then you sort of sandwich it between 1 and -1, and that allows you to get rid of the absolute value. And at this point, it's just sort of almost like a three-sided equation. So if you want to get down to x instead of x minus 1, we'll just add 1 to get rid of the -1. But then, of course, we have to add 1 everywhere else which in this case is a total of 3 places. -1 plus 1 is 0, is less than x, is less than 2. So our radius of convergence, you can see, is actually still 1. Because we're centered at 1, so you can basically go 1 to the right to get to 2, or you can go 1 to the left to get to 0, or you can sort of think of this as the diameter of convergence is going to be 2. And it's going to be centered around whatever we're centered at. So since we're centered around 1, that's why the 0 and the 2 are sort of equidistant on either side of where we're centered. So right now, so far what I've got is that my interval of convergence is from 0 to 2. But the question is, do the endpoints work? Do I want curved parentheses or square parentheses? And I might get one square and one curved, just depends. So now what I need to do is test the endpoints. So the way we will do that is by plugging in the endpoints and seeing what happens. So if we plugged in 2, the upper endpoint, that would be 2 minus 1 to the 1. So we end up with 1 to the n. So the question is, does 1 to the n converge? And the answer is no, because isn't that the same series we talked about on the previous slide? Plus 1 plus 1 plus 1 indefinitely does not converge. So 2 doesn't work. And if we plug in 0, our other limit, right here, then we'll get -1 to the n. So we plug in 0, we get -1 to the n. And like we said in the previous slide, that gives us a 1, minus 1, plus 1, minus 1 forever, which also does not converge, because it doesn't home in on a particular sum. So the moral of the story is that we get 2 curved parentheses for 0, 2. And that's kind of what you'd expect, because once again, this is a geometric series. This time it's centered around 1 rather than 0, but it's still geometric, because we just have something with x in it to a higher and higher power, to a power of n, which is increasing towards infinity. All right, here's another one. Now, if you have your keen eye out, doesn't this satisfy the exact same criteria we just gave, which is that we've got an x, something with an x in it raised to a power of n. So this is yet another geometric series. But hey, why not plug and chug through the ratio test and get really used to it, so that these start seeming like a piece of cake before we go to more complicated formulas. So we need x over 2 to the n plus 1 over x over 2 to the n. Now you might be tempted to start canceling 2's. I wouldn't advise it. And technically they're to different powers, because we have a 2 to the n here and a 2 to the n plus 1 here, so that's algebraically why you can't do it. We need to cancel on like a parenthesis level. So since we have something in parentheses raised to n, that same thing raised to n plus 1, this whole thing cancels that, and we're just left with x over 2 to the first power. And the limit, as n approaches infinity, of x over 2, there's no n's in there, so once again this limit is just going to be x over 2. Alright, so now we can do the second part. Is once we've done the ratio test, now our result, this thing, the absolute value of that, needs to be less than 1. So what we'll do is we'll just once again sandwich it between 1 and -1 to get rid of the absolute values. And now we want to know what x goes between, right? Now what x over 2 goes between. So we'll multiply everything by 2. And that'll just get rid of the fraction and show us the limits of x. So we get -2, less than x, less than 2, which in interval notation would be -2, 2. So the question is, should we have an equal sign in there or not? And that's really what we're talking about with parentheses, right? Curved versus square parentheses. So let's just plug and chug. If you type, if you plug in 2 for x right here, then you'll get, once again, 1 to the n. And we've talked about that quite a bit, that diverges. And same thing, if we plug in -2, -2 over 2 is -1. -1 to the n also diverges. So there you go. So hopefully we're in the swing of things at this point. Plug and chug through the ratio test. Whatever you get, set that less than 1, and you're good to go. Then test the endpoints to get your interval. All right, so here's one. Now, you might be thinking, hey, Chris, fool me 3 times, can't fool me a 4th time. This is not a geometric series, though. So this upper portion, this x to the n, is geometric, but the denominator of n makes this a non-geometric series. And if you listed out some terms, you would see that pretty fast. So once again, when in doubt, do the ratio test first, and then start applying the test. So limit is n approaches infinity. And I'm just going to want to plug in n plus 1 first. So x to the n plus 1 over n plus 1 over x to the n over n. All right, so the n and the n plus 1 don't cancel yet, but x to the n cancels that to just an x to the first power. So if we invert and multiply, sort of get rid of this fraction down here, then we get x times n over n plus 1 and the limit of that. Now, as I pointed out before in the previous video, this x is really a constant. Since x isn't approaching infinity, n is. For the purpose of this little limit problem, x can actually be taken out front, is one way of looking at it. The moral of the story is this limit is approaching x. Because n over n plus 1, as n approaches infinity, that approaches 1, which means we're just left with the x. But you could sort of think of it like this, is that since x is a constant, since it's not going to infinity, and then by L'Hopital's or however else you want to look at it, this is totally approaching 1. All right, so that's what r is. And then the ratio test says, hey, you want the absolute value of r to be less than 1, so that means the absolute value of x needs to be less than 1. So this is interesting. Doesn't this look an awful lot like what we got when we did the geometric series test? We just want x less than 1, which means x needs to be sandwiched between 1 and negative 1 in order to satisfy this inequality. But don't get your hopes up and don't rush to the end and suddenly say, oh, it's like a geometric series and slap on the parentheses. Because it turns out this is one of the ones that's different. One of these, or two of them, is not going to be a curved parenthesis. So once again, we've got to plug in and just see what happens. So first, let's test the right-hand endpoint. So if we plug in negative 1 for x, we would then have this series. Does that converge? Well, you might be thinking it doesn't because it's a harmonic series, just 1 over n, except it alternates, right? Because it's got negative 1 to the n. So when you plug in negative 1 for x, you end up with this puppy, which makes everything alternate. And as we know from previous chapters, the alternating harmonic series does converge. So you actually get a square bracket for negative 1. But then by the same token, when you plug in positive 1, then your formula is just going to be 1 to the n. Oops. 1 to the n over n. And of course, 1 over n is just 1. So 1 over n, and this really is the harmonic series, and the harmonic series does not converge. So that is still a curved parenthesis. So interestingly, when we plug in endpoints, we do get converging for one end, but not the other. And that's because one's alternating and one's not. And that's the main trick you're going to come across when you're finding these intervals of convergence. A lot of times, whether you need a square or curved bracket is going to have to do with whether the thing alternates or doesn't alternate, which can totally save your bacon or save convergence when you're dealing with a harmonic type series. All right, so it turns out that x to the n looked like your standard geometric, but once you throw this bottom on it, it really ends up converging more by geometric rules than harmonic series rules until you get to negative 1. So basically this thing converges as long as x is less than 1, but once x is either 1 or negative 1, it depends on the sign of x. So that's kind of interesting, maybe not that interesting. All right, so find an interval of convergence yet again. This is getting repetitive, but hey, that's good. The more repetitive it gets, the less thinking we have to do on the test, the faster we get through the test. All right, so one thing that's funky about this one is you'll notice we have n plus 1 factorial there, but only an n right here. So that means we're going to have a little bit of a wacky time with the ratio test. But other than that, it shouldn't be too bad. So we've got n plus 1, but n plus 1 plus 1 factorial. So we actually have n plus 2 factorial upstairs. Then x to n plus 1. Then downstairs, when we plug in just n for n, we'll get n plus 1 factorial times x to the n. So it looks a little funky. We have an n plus 2, but everything should still shake out pretty much the same. So if we start, we'll just break out these factorials a little bit so they cancel. So n plus 2 factorial is n plus 2 times n plus 1 factorial. And x to the n plus 1 And then downstairs I just have an n plus 1 factorial times x to the n. Alright, so the x to n's sort of cancel as usual. The power upstairs is 1 bigger than the downstairs, so this goes bye-bye, just leaving x to the first upstairs. And then n plus 1 factorial, cancel n plus 1 factorial, we get n plus 2. Alright, so the question is, at this point we've got an x times n plus 2. And that is it. There is no denominator. There's just a 1 down there. So this is our limit problem, and we need this to be, the absolute value of this to be less than 1, right? But here's the problem. There's an n upstairs. There is no denominator n to cancel this out. So as n approaches infinity, this thing always approaches infinity. There's no way around it. Doesn't matter what x is, unless x was 0. So if x was 0, this limit would equal 0. But any other number that x equals, positive fractions, negative fractions, doesn't matter. N plus 2 is approaching infinity, and infinity times anything besides 0 is going to be infinity. So the only time this converges is when x equals 0. So the radius of curvature equals 0, and it only converges for x equals 0. All right, last one, find the interval of convergence. Not sure where to start, so let's just plug and chug through the ratio test. Limit as n approaches infinity. Now, as usual, I'm going to ignore the alternating aspect at first here. So we will just get x minus 1 to the n plus 1 over n plus 1 over x minus 1 to the n over n. As usual, the powers are just off by 1, so this cancels this, and we're just left with x minus 1 to the 1. And then the n's I don't want to quite cancel yet, so we'll get the limit, or you could, I guess, you may have realized already that n and n plus 1 are basically the same thing as n approaches infinity, because like a million plus 1 is pretty much the same thing as a million. As n gets really big, 1 gets trivial, so these go bye-bye. Anyway, the point is that x minus 1 equals r. The result of the ratio test is what we call r, so x minus 1 is what we get out of this limit problem. So that means that the absolute value of x minus 1 needs to be less than 1 in order for this thing to converge. So x minus 1 needs to be less than 1 or greater than negative 1. And now to solve for x, we'll add 1 everywhere. So plus 1, plus 1, plus 1. So we get 0 is less than x is less than 2. Now I just need to test the endpoints. So the radius and convergence was 1, but we've already got our endpoints, which is 0 and 2. All right, so the question is, do I want square brackets or curved brackets or what? So first we'll plug in 2. So if you plug in 2, you're going from 0 to infinity. Negative 1 to the n times 2 minus 1, which is 1 to the n, over n. So interestingly, this, we already covered that 1 to the n is just 1. So we basically just have the harmonic series times negative 1 to the n. Pretty cool. So, and this does converge. The alternating harmonic series does converge. So it turns out 2 actually works in this case. If you recall in the last one we did, we had the curved bracket on the right. And then the left-hand one, the other limit is 0. So we plug in 0 for x up here, then we'll get 0 to infinity of negative 1 to the n. X minus 0 is negative 1 to the n. And n is still just n. So the only x we had to plug in was this negative 1 right here. So what happens? Does this converge or not? Well, here's what's wild. Negative 1 to the n and negative 1 to the n both are negative at the same time, right? So either they're both positive 1, and therefore they multiply out to a positive 1, or they're both negative, but negative times negative is positive. So no matter what you do, these two guys cancel out. So the crazy thing is that negative 1 times negative 1 to the n always is positive 1, and positive 1 over n is the harmonic series. So the alternating aspect made it converge when we had the upper limit of 2. We have the lower limit of 0, this thing does not converge. So we have a curved bracket here. So the interval of convergence is non-inclusive 0, but it includes 2. All right, so that's interval of convergence. Hope it makes sense. No matter what sort of theoretical discussion you get into about what does interval of convergence mean and all that, you almost never have to use it in a word problem or a complicated situation. Almost all they're ever asking you to do is find the radius of convergence or the interval of convergence. And the only difference, as you've seen here, is the radius of convergence doesn't really care about the endpoints, whereas the interval of convergence, we just have to plug in the endpoints that we get and see if that particular series converges once you know what you're plugging in for x. But ultimately, x, whatever we're plugging in for x, that's just a number we're trying to approximate. So if you're ever trying to find e to the 0.1 using the exponential series, power series, then 0.1 is what you're plugging in for x. If you're ever trying to find the sine of pi over 12 using the sine x Maclaurin series, then pi over 12 is what you're plugging in for x. That's power series in a nutshell. Not the funnest stuff, but at least it's plug and chug. So you have that to lean back on.